Thank you, Ryan, and thanks to everyone who's showing up end of the day. I know it's not easy staying through so many talks, so hopefully we can make this meaningful and exciting for everyone. I'm Vivek. I lead the Applied Machine Learning and AI Engineering team at Cohere. For those who might be unfamiliar with us, a quick primer. So we're a full-stack secure enterprise company. We're led by our co-founder and CEO, Aidan Gomez, who's one of the authors on the seminal Transformer paper. In terms of our offerings, so on the left, we have our generative models, with Command A being our flagship current SOTA open model. On the search side, we have the embed and re-rank models. These models are multimodal, multilingual, and have consistently been SOTA in the industry for many years. Then we have Compass, which is our packaged offering that's focused on your data ingestion, maintaining your enterprise security credentials, chunking, parsing, basically preparing your data for all knowledge augmentation tasks. And finally, we have North, which is our agentic development platform. All of these products can be deployed in your secure private environments, in your cloud provider of choice, or on premises. We also let you customize these models all the way from continuation pre-training of the base models to post-training of the models with your private enterprise data. Cool. So jumping into our talk. So 2025 is turning out to be a pivotal moment for AI agents, a convergence point for where possibility is meeting practical reality. We have seen an unprecedented acceleration with all of these systems in the last several months, making truly autonomous systems a possibility. Reasoning models have crossed critical thresholds, allowing them to plan, evaluate, and act, mimicking many of the human cognition abilities, but also surpassing many of our limitations. Additionally, the investments in test time compute have meant that these models can now think longer and harder about some of the most complex tasks, thus reducing the error rates and increasing their performance on these capabilities. Finally, the engineering investments in these spaces means these models are now accessible beyond some of the largest tech giants. What makes this moment really exciting is we're finally at the point where we can move past some of the reactive AI assistance to proactive human-AI collaboration. So the challenge in front of us is not if these systems are going to be are going to be possible, but how are we actually going to build, architect, and deploy these systems into production? And that's what gets me up in the morning, personally. So as we start talking about them, let's take a moment to talk about what we mean by agentic systems. I've always found it interesting to look at how various industry thought leaders and various companies are defining these systems. I've listed 4 definitions that caught my attention from various industry luminaries. The first one says it's a model plus instruction plus tools plus runtime. Another one says it's a router and skills and memory. Some others are saying it's a model plus memory with planning and tools and with a while loop, right? So what's interesting is these are not really divergent ideas. They're all building on the same fundamental concept that agents are systems that can observe an environment and then take action on that environment. All of these nuances are then different design patterns on how you're trying to implement these systems that are building on the foundational blocks of planning, reflection, tool use, memory, and multi-agent collaboration. Before we rush headlong and into the excitement of building these agents in 2025, let's take a step back and see how we got here, right? So we started our journey with a lot of these level 1 systems. So that was the direct LLM interaction, so basic, simple Q&A systems or writing assistants. And then we moved to enhanced systems that you gave knowledge-based access to your LLMs, right? So your RAG-based architectures from where you could build, for example, a customer service bot, which would be human in the loop, or with guardrails directly deployed in production. Then you moved on to tool-augmented systems. So think of your narrow NL to SQL style capabilities. So the key insight is there are many valuable business applications in this realm, and that continue to hold true. You could still have millions of customer service chatbot interactions with a level 2 style of system, or a level 2 plus level 3 style of system, and you don't always need an agent. Right? So level 4 is where I consider the basic agentic stuff starts. So it's basically self-directed tool use based on the task requirements, and that's where your LLMs are bringing in the planning components, right? And beyond that, we get into all sorts of complexities with goal-directed behavior. So all of this does not obviously come for free, right? There's lots of complexity, unpredictability, and high amount of token costs that these systems bring. So before building an agent, I think a key question that one must ask themselves is, does your task at hand really need autonomy and exploration, right? Because if that's true, then yes, you need an agent, and which is why coding or deep research are currently really popular applications of these systems, right? Or sometimes you might need a simpler workflow-based system, right? Because every impressive solution is not always the most practical one, right? And as with all of the AI systems that folks have built in the past, it's really important to align the business value and justify that with the implementation that you're going after. Cool. So let's dig into the enterprise challenge with building these systems. If I were to sum it up, for me personally, this one graph summarizes the challenges that you run into with these production-grade systems, right? We're not really building systems that are simple one-step agents in production, right? These agents likely have to gather lots of data, analyze, synthesize them, and then also take action across multiple of these systems, right? And this graph illustrates why that might be a problem, right? Consider a system that has an impressive 99% accuracy on a per-step basis, right? With an agent that is now going 20 steps deep, what that means is you're going to run into an 18% failure rate for your overall system. And if you have an agent with a 95% accuracy on a per-step basis, which seems acceptable in most production systems, that leads to over 2/3 of all of your calls failing, right? And this has real practical business implications. So the implications are clear, right? You need to solve 3 fundamental problems. One is, how do you increase the per-step accuracy of your agent? 2, when you have an error, how do you validate and recover from that error? And 3, how do you prevent cascading failures of these systems, right? Because the curse of complexity over here is not something theoretical, it's really mathematical. And if you are going to build a system, these principles need to guide all of your designs. Because simple tasks, again, don't really need agents. Let's actually take an illustrative example to walk through what those challenges might look like, right? So let's assume you're working at an e-commerce company, and in the excitement to replace humans or augment them, you've been tasked with building an agent for analytics. So you've built a said agent, and now your C-suite goes in and types in a query, which seems fairly straightforward, which is find the product categories that are underperforming compared to the last quarter, right? And identify the potential reasons for that. So broad strokes, let's assume that the agent that you've built comes up with a plan that's 5-stepped. First, it tries to figure out what this intent means. Second, it's going to try to transform that query into some form of data retrieval. Next, it's going to do some amount of analytics. After that, probably do some market correlation, and finally would generate the insights, right? So step 1, so it's converted this intent. It's identified a metric, it says revenue, the dimension, the product category, and then also a time period, quarter over quarter. Therein lies your first challenge, right? Is underperforming units sold, or is it revenue? You might not quite know, right? Unless either you're a subject matter expert, or you know the actual intent of the user. And this is where a combination of like product design and intent breakdown becomes critical. In the next step, let's say once you've successfully mapped the intent, you've tried to retrieve the data, but you probably didn't understand all of the schemas accurately enough, right? So it's quite possible you have some missing join conditions, which leads to incorrect retrieval of like the data or causing incorrect relationships, which then get translated into your next step with the analytics. In the analytics itself, what's happening is you're trying to aggregate this information, and you're trying to average out what was the actual error percentage. Because you're dealing with percentages, and you didn't deal with the average discounting. That could be another failure. And then in the market context portion, let's say you didn't account for seasonality with the sales of your products, right? Which is something a subject matter expert would know, right? This is, again, going to cause an error. And finally, once you've synthesized all of this, it's often, even as humans, important for us to understand what's an actual correlation versus causation, right? So as you can see, even something that's seemingly basic, 5-step process is running into myriad of like challenges, right? Like that you have to deal with. So this is not to like dissuade us, obviously, to build with agents, but it is important to understand these like failure modes and plan for them, right? So the first step that I often like to use when I'm building these agents is my critical defense against the curse of complexity, right? Which is try to use the largest possible model that you have access to. Because just going back to that graph, right, even a small bump in accuracy on a per step basis from, let's say, 98 to 99% means you've dramatically changed the outcome that you could be getting. What I often see folks trying to do in production settings is they start the other way, where they're trying to optimize. They start with the smallest model and then are focused on like inference, latency costs, or cost of like running the system. But what you're really sacrificing, or shouldn't sacrifice, is the reasoning capabilities of these like models when you're trying to build the first version of this product. Going the other way from a large, expensive system and then optimizing that via distillation, caching, batching, or all of the other techniques is much simpler than starting with a smaller, less powerful model. The next one is to focus on test time compute, right? So it's important not to get into a faster is better mindset when we're building these like agents. It's important to allocate the right amount of like resources so that these models have enough compute to be able to reason, think through, try multiple approaches, handle the errors, and recover from them, right? As a human analogy, let's assume you have two test-taking students, one of whom is rushing through all of the questions and giving certain solutions, another one who goes through the process of answering them, but then goes through a second round of trying a different approach and checking every answer. The latter is obviously going to have a higher probability of success. The same is true for these agents, right? So the inference cost that you're accounting for here is not just like overhead, it is a critical component of like the reliability of your system over there. So going back to like the SQL example, I then ran the model in a reasoning mode, so you can see a bit of the trace over there. So the model's actually trying to think through, hey, what are exactly the steps I need to go through, and what sort of like the correlation between certain tables, which would help it catch some of the errors, right? The next one is, in terms of tips, is focusing on the context, right? So this, I think, is like fundamentally really important and differentiates successful implementations from unsuccessful ones. Because every model has like a limit, and it's not about its like reasoning capabilities, it's about the context window. And now that window might be small or big, but there is a limit. It might be 8K, it might be 100K, it might be 200K, or it's 1 million, but there is a limit. And the model knows what it knows in the bounds of that like limit. So if you're trying to get it to do something that does not fit in that context window, you might have problems. And understanding this like limitation and designing your system based off this fundamental principle is going to prevent a lot of pain points later. Additionally, a key part of this context is not just the data, but it's also the tools it has access to. For example, if you expect your model to be retrieving or adding data to a specific database, and if it didn't have like that tool access, no amount of like design is going to like save you at that point, right? So again, going back to the human analogies, many times when we run into problems, we're asked to empathize with the person on the other end. So I'd actually suggest also empathize with your agent. Try to think if you had a 100K context window, and if that was the limit, how would you make a decision, right? And using that as a first principle will probably save you some amount of pain point and success in deploying these agents. Closely tied at the hip to the context step is breaking down these complex tasks into multiple subtasks, right? So now, it's important to remember that this is not going to change the overall number of steps, but what this is going to do is help you catch and validate errors and also prevent cascading errors. So going back to our SQL agent or analytics agent example, you could probably have sub-agents over here that are focused on data retrieval or correlation analysis or insight generation, right? Now, what that helps with is in the data retrieval agent, you could have stuffed all of the table schemas in the context, or that would ensure that the model has all of the operating information to build the right schema design. And also, you could be building validation and error checks that are specific to the data retrieval portions, and so on and so forth for the other sub-agents that you're dealing with. Which brings us to the overall data and tools challenge. As a quick recap, why did we even bring in this concept of like tools, right? These models have many fundamental limitations. While they're great, they have issues like knowledge cutoff, hallucinations, and computational weaknesses. So tools is our mechanism to giving superpowers to these models. And like all AI systems, these agents are also as good as the data that they have access to, right? So data curation over here is not just some form of a preliminary step. It is an ongoing foundation that is going to ensure that your overall deployment is successful. And tools can enhance this overall process, right? They give agents the ability to work with production-grade data sets that have been algorithmically cleansed, have been validated, and have been transformed and ready to use in your ecosystem. But they're not like a magical solution, right? It does not fundamentally change the human need to go in and be the subject matter expert and design and architect the data systems itself, and then also design the right tools that are going to augment your LLMs, right? And then the tools themselves run into many challenges, which I like to draw this parallel with microservices. For the folks who've had to deal with gnarly C, C++ libraries before Google or Stack Overflow existed, it's pretty painful, right? Like if you have to read documentation that is not sufficient or try to decipher what input-output parameters mean and how error handling is done or what a particular error code does. And LLMs are going to run into exactly all of those same challenges if you are not going to be doing a great job of like documenting these things. So making this into a concrete example. So let's assume you've built a financial analysis agent. It had access to 5 different tools, right? And each of those could potentially have their own problems. Your classic issue with like date type format issues, mishandling of like specific subject matter data, or you got a cryptic error code, 4302. As a human, you probably don't know what to do with it. Neither will your LLM know what to do with it, right? Or no validation errors on each of these like inputs. Again, all of this like really needs to be documented and be told how your LLM should be handling it. So again, the key insight or tip I would have for you over here is be super explicit when it comes to your contracts and documentation. Create open API-like specifications for each tool. Standardize the error responses. Make sure you're having sufficient amount of examples for both like valid, invalid outputs, error cases, And when it comes to versioning, make sure you have explicitly versioned each of these like tools, and all of that context is passed into your LLM for having a successful deployment, right? So tying all of this like together, right? A successful implementation is not going to eventually come down to a single tool or single context, right? It's going to come back to the implementation patterns across your entire ecosystem. So it's important that there is some form of a feedback loop over here at play, such that your overall agent and agentic system is getting better, both with like monitoring, human intervention, or in the future, hopefully, self-learning systems, right? A second tip or pattern that I really like to use is the one with like query rewriting. This often comes in like very handy with ensuring that you're capturing the right intent with what a user's question was or user's input was. And then if your product allows the ability to even edit or change the transformed query, that's even better, right? And when it comes to tools, candidly, I don't think any of these models do great if you're going to give it 50 or 100 tools, right? Most of the models do well if you're going to give them access to maybe 5 tools or like maximum of like 10 tools, and they're acting on some amount of like narrow capability. This is, again, why the whole sub-agent paradigm comes handy. So trying to strive for narrower systems is your way to go right now. Which finally brings us to evaluations, which could be its whole talk in itself, but I'll try my best to compress it in a few minutes. Why do we need evaluations? Obviously, we want to do performance and benchmarking, any insights for improvements, understanding our like goals and progress towards it, and overall safety and reliability of these systems, right? These evaluations were complex enough with just basic LLM interactions or RAG-based systems, but get exponentially more complicated when it comes to agents. So if you take a single-step agent, right, like what makes a successful agent? It's actually going through many different things, right? So first, it's going through the process of like relevance, where it's determining if a particular function or action is needed or not. Then it's trying to route it. So it's basically trying to understand what is the specific tool that you need to pick. Then it needs to actually execute the said tool. It needs to decide and parse the inputs and outputs. The model also needs to reason. The model also needs to course correct. Now, that's a lot of different things across a lot of different scenarios. So evaluating this is really, really complicated. But without having good evaluations, again, all you're going to be left with is wipe checking on agents, and that's not sufficient, while it's important to have it along with true LLM evaluations. So again, taking a concrete example, let's say you had a simplistic tool call, which was, hey, tell me about the weather in New York on a particular date, right? So what's happening under the hood? Let's say you had 3 different tools. So your specific system had to decipher what was the right call over here. In this case, it had to be the get weather info, not by coordinate or by city, let's say, or by city name. And it needs to pass in the city name over here, also give the date time in a specific format. It got back a return response, again, was like NL. So you had to parse out the right bits of information over here and pass that on to the next step of the system, right? So it's important that your evaluation then handles this, right? So you should be able to both test that, hey, you're calling the right tool, and then also the right execution. And that's how you build a reliable system, by decoupling these evals. So finally, when it comes to failures, and you're inevitably going to run into failures with any of these systems, in practice, my team and I have found this to be a bit of a helpful guide for us to determine like next steps. If you're seeing, let's say, low severity failures, especially with like tool calls or function calls, like maybe prompt engineering is your best solution over there in terms of like move forward basis, right? If you're running into slightly a medium amount of failures, let's say 10 to 20%, and that's around parameters or formats, a targeted annotation campaign to improve your model should probably do it. Anything beyond that, you're likely looking at some amount of complex model fixing process. Okay, to tie all of that together, so first off, agents are not all you need. Keep it simple. Don't optimize too early. Data context really matters, and evals are still key. So thank you so much. That's my talk.